Hello, welcome to the very first video of the Further Studies Mathematics course. And the very first topic that we'll be looking at is continuity of functions. So if you're watching this video, it means you're either a Further Studies Mathematics student or teacher, or you're someone who's pursuing a math-related course out there and you want to really excel at what you do. So I'm here to help you do that, and I'm here to enrich your understanding of this beautiful subject called mathematics. Okay, so continuity of functions. Before we even get to the formal definitions, I would like you to have an intuitive sense of what this topic means and what it represents. And by so doing, we're going to use functions that we've already established or we've come to work with so far: the linear function, the quadratic function, the exponential function, the hyperbola, to work with, this, just to start us off in terms of our discussion as to what we'll be working with. So if we sketch a linear function, we know that by now it's a straight line, okay? So we can do that without lifting our pen from the paper, from the pad, or from the board. And that can represent a sketch of some linear function. Okay, what about the parabola? If we have a parabola that we need to sketch, we can do it at one go without lifting our pen again, from the material that we're drawing on. What about the exponential function? Okay, we can draw the exponential function there without lifting our pen as well. Okay, what about the hyperbola? Okay, so we know by now that it has two curves, one curve there and perhaps some other curve there as well. Obviously, it's always cross-quadrant type of positions or in that way, okay, depending obviously also on the horizontal and vertical asymptotes. Now, what do we notice? The linear function has no breaks. It is continuous along its domain. Okay? The parabola has no breaks. It is continuous along its domain. Okay? The exponential function has no breaks. It is continuous along its domain. But when we get here, the first arm here, or the first curve here, is continuous up to a point. All right, so let's start with the definition, okay? A function f is continuous at some number c if the following happens. Limit as x approaches c of the function should be equal to the functional value at c. Okay, so it means here, if we dissect this and break this down, there are three different conditions that should be met for continuity to really be concluded as a fact for that particular function. What are those three conditions? Okay, so f of c must be defined. Okay, so we mean that there is a point in the domain of f where x is equal to c. Okay, so c is not outside the domain, it's inside the domain of f. And b, limit x approaching c of the function f exists, and this means two things. The limit from the left and the limit from the right exists, and they are equal to each other. Okay, and the last condition is that a and b must be equal, right? Limit of x approaching c of f of x must be equal to the functional value at the same point, c. So those are the three conditions that must be met before we conclude that a function f or any other function is continuous at a given point, right? So when we prove continuity, we must talk about the functional value and also the limit and show that there is equality when it comes to their relationship. Okay, let's jump into examples now. All right, so here we go. Using the definition of continuity, show that the following functions are continuous at the given number c. So given a polynomial here, we need to show that this polynomial is continuous at c is equal to 1. Okay, so what must we do? Let's start with the functional value. F of 1 will be 3, 1 times 1 to the power 4 plus 6 times 1. This will give us 9. Okay, let us test the limit now. Limit as x approaches 1, okay, of f of x, what will this give us? We can substitute, this will be limit x approaching 1 of the function here. This will be 3 times 1 to the power 4 plus 6 times 1, giving us 9. Therefore, we know that limit x approaching 1 of f of x is equal to f of 1. And therefore, it means that f of x is continuous at that point, at c is equal to 1. Okay, so that is how you work with continuity and show that the given point c is actually a point in the domain. In other words, it gives you a real number in return, in the range of the function, and the equality therefore talks about the fact that those two quantities are therefore equal, which allows you to conclude that f is continuous at that particular point where your x is equal to c and the c being 1 in that case. All right, so this takes care of the first example. Let's go to the second one. Okay, our given function here is e to the x, and we are going to test that at c is equal to -2. Okay, so what do we need? The functional value, you have -2 is e to the -2, giving us e over e squared. 1 over e squared. Right? Limit as x approaches -2 of e to the x will be e to the power -2, same as what you got, 1 over e squared. Are they equal? Yes. Therefore, limit x approaching -2 of g of x is equal to g of -2, and this allows us to say now g of x is continuous at c is equal to -2. So the structure is very important, especially in further studies mathematics, because notation is highly penalized, and you want to ensure that you are structuring your work in a logical but also a mathematically respectable way, using the right symbols and the right notation throughout. So that basically tells us that g is continuous at this point. X is equal to -2, but obviously you give it a particular variable to just say is an arbitrary number or a random number that we'll have to test if really that function is continuous at that particular point. So this takes care of example number 2. And I should have written 2 here, but then this is example number 2. Let's go to example 3. Right. Number 3, we're given a rational function. Okay, and we are going to work with c is equal to 0 and show if h is continuous at that point. Okay, so what do we need? H of 0. Okay, let's see. 2 times 0 minus 3 times 0 squared over 2 plus 0 cube. Okay, what will this amount to? 0. Okay, limit as x approaches 0 of the rational function will give us 2 times 0 minus 3 times 0 squared over 2 plus 0 cubed, which will also give us 0. And therefore, we know that limit as x approaching 0 h of x is equal to h of 0. This equality means that h is continuous. H of x is continuous at c is equal to 0. Okay, so at that point where x is equal to c is equal to 0, we have that h is continuous. Good stuff. Let's go to example 4. Right, k of x, we're given a root function here, and we're going to check at c is equal to -5 if it is continuous there. Okay, so we go k -5 is equal to -5 squared plus 4. So that will be 25 plus 4, giving us a square root of 29. It's a real number, so k is defined at that particular point. Limit of x approaching -5 of square root of x squared plus 4 will be equal to square root of -5 squared plus 4, giving us square root of 29. So there's equality there, and therefore limit as x approaching -5, k of x is equal to k of -5, and therefore k of x is continuous at c is equal to -5. Okay, so that's where we're at in terms of example 4. Let's do the last one, a piecewise defined function, and see how we approach that one. Okay, number 5 is a piecewise defined function, and we have a quadratic function and a linear function here. So it will give us a quadratic function if x is greater or equal to 2, and that is the domain of the quadratic function, and the domain of the linear function is when x is less than 2. Where are we testing continuity? At this number, at this point, where c is equal to 2. Okay, so what do we need? The functional value first. P of 2. So which one are we going to pick? The x squared, because it includes the 2 there as the endpoint of the restricted domain. So that will be 2 squared, giving us 4. Okay, what do we need to test? The limit. But now, because we have 2 different types of functions, one on the left and one on the right, we need to find the limit on the left, the limit on the right. If they are equal, it means the limit at the point exists and it is equal to the value that we get. Okay, if it is equal to 4 as well, then we'll say that p is continuous at that point. Good. So let's go. Limit as x approaches 2 from the left. Okay, 2 from the left, that is the linear function. So we end up with 2 plus 2, giving us 4. Limit as x approaches 2 from the right, we have the x squared. So we end up with 2 squared, giving us 4. Therefore, limit as x approaching 2 of p of x is equal to 4, right? So that comes as a deductive statement from saying those 2 are equal, and therefore the limit exists at that point 2, because the left and right limits are equal. Now this 4 is equal to that, and therefore we have that limit as x approaching 2 of p of x is equal to p of 2, and therefore p of x is continuous at c is equal to 2. Right. So that is really the 5 examples that I have prepared for my presentation. I believe they were valuable to you, and I thank you for tuning in and watching the entire video up to this point. So if you need to, watch the entire video again and just ensure that you reinforce understanding in your approach in terms of continuity. Right. I'll see you in the next video when we discuss discontinuity of functions. Thank you for tuning in.